Yeah.
Okay, so I believe we already went through this problem before, but let me just resolve it, and I'll tell you how to approach the solution.
Yeah, this problem was like, this problem was on the test actually. She pulled this
Okay.
test, but then like I looked at it and I looked at her way of solving it, and I was really confused because there's like a lot of the main part of confusion is I understand how to do the problem if I know which direction to put the currents, because there's three different
Okay.
EMFs. And I thought that like normally the biggest EMF, if you have two EMF, you just determine the direction of current from that. But for this one, it's a little bit weird because there's three, so that means there's three different currents as well, like current one, current two, current three. And I was a little confused on like which direction they would all go.
Um, if you solve the problem, then the answer is just, I mean, there's lots of different ways to actually solve this problem, but always the right answer is just one. So if you solve it and if you properly just assign the direction of current with respect to the direction of the loop, then you should be able to find the right answer. As I said, if depending on the sign of the current flow is provided into the given circuit. So you have to find the relationship between the direction of batteries, direction of EMF, in terms of the current flow along the circuit. So as I said, it doesn't matter which direction you set up the loop of each current. Um, as long as you have right relationship between the EMFs and resistance, you should be able to get the right answer. So I'm gonna show you the two different ways. I mean, it should give you the same answer, but depending on the which direction of the loop with respect to the current, the formula will be slightly different, but the answer should be same. So let me give you the way to solve it. So the for first way, I mean, okay, let me just write it. So now you have basically two loop, right? So let's assume that you have loop one, loop two. So I did the bottom, the loop with R1 is loop one, and the uh, the loop with R2 can be called loop two. So in case you set up the loop two with counterclockwise, then um, for loop one, and now you see that the current floor, if you set up so for loop one, the bottom one, and your current floor, you can assume that the direction of current is I1, and that direction, the current flow is I2. So you have basically two mainstream of a loop. So you can actually physically separate I1 along the E2 and I2 along the E2 is separate current. Later on, you got to just add them together as a single current path. But let's just separate. Let's just assume that there are two separate current flow along the E2. So E2 on the loop one is E2 minus I1 R1 equals 0 because you see that the current flow is the same direction of the loop. So the based on the junction rule and the loop rule, you have to have the E2 is positive value and R1 should have negative value together. So that value of this potential uh, difference along this loop should be equal to 0.
Wait,
That's
why would it be I1? Wouldn't it be I2 because it's going through EMF 2?
what
Yeah.
this is loop 1.
But I thought the current, like when you number the currents, it correlates to like the EMF that's there.
So it is current right I1 is along this loop.
Wait, because there's EMF2 in the loop, right? Wouldn't it
Right.
be I2 instead? Because that's the current that's going through the EMF.
So as I said, we gotta separate this circuit and this circuit physically. Then we'll just I'll get to that point. Okay. So let's assume that you have I1 along this circuit, complete circuit. Okay. So you have one current along this. Let me just fill it up one more time. Hold on. So this is a loop, two loop. So let's assume that you have two separate paths. I mean loop one and loop two. So along the loop one, there's current one going along this path one, and loop two. This is loop two, and this is loop one. Loop two has only one current, the I2. Let's assume those two separate paths for now, and later on, I'll just show you how that those current combine at the uh, along the path along the E2. So here is from this I1 is E2 over R1. Okay, so that is first one. So you plug that numbers into this formula, that is 5 volt divided by 100 ohm, that's 0.05 amps. And loop 2, as I said, this I2 go along this loop 2 goes along this loop 2. So that is I1. Okay, so let's assume that first assume that current goes counterclockwise, flows counterclockwise. That's I just assumed for now. So E1 is positive, and now E2 and E3 is face against that the E1. So that should be E minus E2 minus E3. And now R2 is also same direction, positive direction with the current flow I2. That should be, so I2 R2 equals 0. So you have to just make sure along any direction of the current flow, E2 is opposite direction of E1 is opposite direction of the E2 and E3. E2 and E3. So it doesn't matter which direction you choose, the sign of E2 and E3 should be always opposite to the E1, the one of the E1. So now from this one, I2 is E1 minus E2 minus E3 over R2. So here E1 is 6 volt, E2 is 5 volt, and E3 is 4 volt. Divided by R2 is 50 ohm. So that is now how much? That is minus, I think 3 volt divided by 50 ohm. So that is minus 0.06 amps. So E2 along this loop 2 is minus 0.06 amps, 60 milliamps. So minus sign means the current must flow clockwise, because the direction I choose is not right direction. That's why I end up with the minus sign in my value of current. So in terms of the sign of the current, the I2 must be clockwise, because I just assumed that the I2 was counterclockwise, and now result in the minus sign like this, right? So this indicate the I2 should be clockwise. So from that, now I have to rechange the direction of current this direction, right? So now let's take a look at the current flow along the A to this point, 2 point. So one current I1 produce zero point 0.5 from right to the left, right? So right here, I1 is 0.0, how much? 0.05 amps. And I2, same thing, same direction from right to the left. I2 is 0.06 amp. So the along this junction from A to, let's name that this one is C, from A to C, or I mean, sorry, C to A actually. C to A, two current flows actually flow the same direction. I1 is 0.05, 50 milliamps from C to A. I2 flows C to A2. So your total current along the C to A, total current C to A must be I1 plus I2. That is 0.05 plus 0.06. So total current at that point must be 0.11 amps, so like 110 milliamps. So from point C to the A, I, C to A is 0.11 amps. Okay. So from point A all the way across E1 back to the point C is 60 milliamps. And now when the current reached to this junction C, then that produce that combined with the I1 and then flows the 111 milliamps to the A and then separate to I2 and I1. Okay, that's the first way to solve because I choose counterclockwise as of the direction of the loop 2. Okay, so the three current floor I1, I2, and the junction between the C and A is given by this way to solve the problem, right? And you can also try the different way. If you choose clockwise, let me clear up, then just I will show you how to solve this problem again. But pretty much the same as before, but if you choose, do you have any questions so far?
No, I think I understand how to solve the problem. I'm just confused on like my teacher's way of solving it because she used three different currents and I didn't understand like how she determined that.
I mean, that's as long as your teacher stay with the same rationale, that's fine.
Yeah, but she put like current I1, I2, and I3, and I was confused like where she got that. And I included the screenshot of her work on the email if you wanted to look at that, but I was confused on where she got that.
Did the answer the same as this one?
I think so. The answer is correct. I just don't understand her work.
I mean, that's so basically, the as long as you're just as I said, to stay with the same. I mean, is there a reason that you
I
you
know
have to
how to,
only stay with the same weight to solve it?
no, I know how to, I can solve it in different ways. I'm just like, I just want to understand like how she solved it. Because when I was looking at her explanation, like it didn't make sense to me.
Okay, well, let's take a look then. And let me just finish this second part first. and then we can get back to that the way to, your teacher solved. And if it is wrong, then I'll tell you that's wrong. The good, right way or wrong way. All right.
Hmm.
So hold on. Let me just one more time. The same thing. You just do the same way, clockwise. Loop two, and this one is loop one. So before it's moving to the next, second way to solve, I mean, the different way to solve this problem. Um, did you did your teacher actually just show that the way of solving the problem, and did she actually take into account the solution, the way of solve the problem as the credit for the problem, partial credit or something? Does she want student actually solve the same way her actually solve the problem?
No, I don't think it matters. But I just like when I want to be able to understand like her work. So when I was looking at the solution that she posted, I just didn't understand it. But I know that I can do it in different ways too.
Okay, so if you just solve this problem the different way and you got the full credit, or
Yeah,
she
I should be
just
able to, as long as the answer is correct, it should be fine, and the work is correct. But I know there's different ways to solve it, but I
because
just
the reason I'm keep asking this is because I saw that your answer, the second, third is wrong.
on the teacher's work.
Yeah,
Oh, I
so
don't
that's
know.
what.
That was just her work. So
Yeah,
I
I don't think that your teacher, because at least based on my knowledge, that just, I mean, there's. Let me just actually. Right, then let's just, okay, so you said that how do you solve this problem, right? So let's get back to your email and see that. Okay, so, right, which part you don't understand? And this
I
one, the
don't.
blue, green loop is fine, that's okay, that's correct, okay? And the blue loop, let me check. E2. Okay, just tell me which part you're not sure.
I'm not like entirely sure why she did current two, current three, current one, like how she got those values.
So I3 is the same as I said, I3 is the same as the current floor of the IC from C to A, which I actually already show you. I3 in this year, I3 here, the same as IC to A, the one I actually, so
Oh, she just labeled it as a separate current instead
you're
of just.
right, right. So that's probably just the same. So you got the same, the 1110 milliamps. That I3 is exactly the same as ICA, the one I just showed you.
Okay, I think I was just confused on when she added the second
Mhm.
current. Wait, wouldn't the I3 be um actually, wait, just like a general question, are the
Mhm.
current, like when you label the currents like I1, I2, is
Mhm.
it corresponding to the resistor number? Like resistance 1 goes with current I1.
Not always, but it's more convenient if you just label the name of current same as the name of resistance. Then makes more sense, right? That's easily solve the problem based on the same conventions. So
Oh, okay. I think I get her work now. I just didn't understand where I3 came from, but it's just I1 plus I2.
yes, just one plus two. That's so I instead of I3, I instead of she actually labeled that as I3, I just labeled ICA because C is junction between current I1 and I2, right? From the B to A. So that's why I just labeled different way, but that is the same as I3.
Okay, that makes sense. Yeah.
Okay. Does it explain everything?
Yeah.
Okay. All right. So as I said, that it doesn't matter. doesn't matter which direction you choose for loop of current, as long as you stay the same convention and the same sign for EMF, EMF, then you should be able to get the right answer. It doesn't matter you choose the wrong direction, your current floor, the final answer will tell you your choice of the direction of the current is correct or not when you completely solve the problem. So it's just like a degree of freedom. You don't have to too much worry, but as long as you stay with the right relationship between the EMFs and resistance based on the junction rule and the loop rule. So junction rule, loop rule itself, especially the loop rules, indicating that the relationship between the circuit elements. Okay. So now, as I said, that's as long as E1 has different sign than E2 and E3, you should be good. Okay. All right. Then second question, right there. So number 11. So initially single resistor R1 is wired in battery. Then the resistor R2 is added in parallel. Are the potential difference cross R1 and the current I1 through the R1 now less than or the same as previously? So is the equivalent resistance R1 to of R1 and R2 more than, less than, or equal to R1? The total current through the R1 and together more than, less than, or equal to current through the R1 previously. Okay, so let's get back to here. So I believe you originally have the single loop of the circuit, DC circuit. So only have R1, right? And this is B N, that's plus N minus. Now you suddenly just add one more resistance to the circuit like this, right? In parallel.
Mm-hmm.
R1, R2, and this is B. So basically, you can think of the potential difference between R1, I mean, along the circuits, like this is could be like A and B, and let's see that this one C and D. So you can think of the potential difference between A and B as this B1, and potential difference between the C and D is B2. So basically, now currents from the EMF flows along the junction A and split into the I1 and I2. Okay, so basically I now originally was just, if you think of the current along the resistance one is I1, and originally that I is the same as I1, but once you add resistance with the second circuit pass, then I becomes I1 plus I2. Kind of like a current is split into two different passes of the current floor. And now potential difference from this circuit should be maintained. So V is same as V1 plus V2. So with that relationship, if you add that here, so you re-express this junction rule with the voltage and the potential difference and the resistance. That should be over R12 is V1 over R1 plus V2 of R2, right? So now B, you apply this relationship, then that should be 1 of R1, 2, the same as 1 over 2 R1 plus 1 of R2. So if you rearrange it, then R1, 2 is the same as R1 times R2 over R1 plus R2. So that is same as R2 over R1 plus R2 times R1, right? So from that, if you look back the questions, oops, the first one. So the first question was the potential difference across R1 and current flow I1 to the R1 now more than. So basically V1 is same as before because potential difference doesn't matter whether you just add more resistance in parallel, the potential difference between those two junctions must be this must be same. But I1 obviously should be the less than before because split, I mean, the current, basically previously the total amount of current flows is the one pass of the circuit, but now that is split into the two circuits, so I1 must be less than before. Some amount of current flows in the I2 with the R2. And R12, yeah, obviously R1 must be bigger than R12, right? Because as I said, R12 is R2 over R1 plus R2 and R1. So from this relationship, R1 must be larger than R2. Okay. And then DIT is what? That is total current with R1 together. Together more than less. And I can see. Okay. Equal to the current. Yeah, that the total current should be
Yeah, the total current is more than R1, like
right,
I1 alone.
right, right.
But
Because
I don't know why she said for B the current for I1 is the same.
no, it cannot be same. Just like because you add the separate paths, right? So total that conservation of the current there if you add more separate current paths, then the amount of current flows into the I1, R1 must be less than the one with the single path of the current flow. So R I1 should be less than before.
Yeah, but her reasoning, like if you look at the next question that I asked for number seven, like
Mm-hmm.
7B, I was confused too because she said that the current is less when you add a resistor in series. So technically for according to like the different rules, if you add like a resistor in
No,
series, the
that's
current is
that B
different.
is not correct too. Number
Yeah,
seven.
that's
B
what
is,
I was thinking. But
so maybe she I don't know why she answered that way, but I1 should be same for number seven
yeah.
because the current along that circuit, as long as the circuit wire does not have intrinsic or internal loss, doesn't matter how many resistance you add in the circuit, your current total amount of current must be conserved. So I1 must be same before and after the resistance added into the circuit. So the B, I should be, I1 should be the same.
Yeah, that's what I was thinking. I'll like
Yeah.
ask about it when I come back to school because I don't know why she wrote that.
Okay, well, just go ahead and twisting your, arms of your teachers then. Okay, so I mean, just kind of quite clear. I mean, this is like, you know, DC circuit, 101, the basic rule of Ohm's law. So, you have one single pass, unless there's like an intrinsic loss of the circuit wire itself, then total current must be same. Doesn't matter with additional resistance or not. So if you look back, this is pretty straightforward, especially the circuit series circuit. is even more simple, even simpler than the parallel circuit connection. So if you have like one now is condition is like you have EMF, and you have one resistance R1, and now you add just suddenly add one additional resistance, and this is now is V, and you can think of this one is also like a V1, and now you add the second resistance are V1, and this one is V2. So by adding the second resistance, you create more potential difference between maybe point A and point B. This is R1. So this I, that current along this resistance I1, along this circuit is I2. So basically, I is same as I1 and I2, and the V is now by adding the one more resistance, you create a more potential difference between those two junctions. So if you basically that B1 is less by adding the more resistance, and the B I is I1, I2, same as before, same. And the C, V is V1 plus V2. You can just actually just replace it with the, expression of the current. So, and resistance, that is IR plus I1, 2, R1, I1, R1 plus I2, R2. And now the I the same as I1 and I2, so you cancel. And then obviously the R12 is R1 plus R2. So obviously R12 is bigger than R1. So the more resistance added into this equation. So this number 7 is pretty straightforward. And the answer is just like you have less amount of the potential difference on R1. So, and then same current along the circuit without additional resistance, and the potential difference, because due to the potential difference change, then you have more amount of resistance in the circuit. Okay.
Yep.
All right. That's all you have, right? When your question from your test. Okay. Do you have any other questions?
No. I took my magnetism quiz last
Mm-hmm.
week,
Mm-hmm.
this unit, but I didn't understand like anything about because
Ah,
she tested us the day right after we learned the unit. So like we just started, so I had no idea what was going on. Like all
hmm.
I remember was like the magnetic force is equal to like VQ um,
Mm-hmm.
times B times cosine theta, and that was it. But the check
Uh-huh.
was really hard, so I think I need to like
Okay.
learn a little bit more because I have to retake it when I come back to school.
Also, your school teacher allowed to retake the test.
Yeah,
Okay,
retake.
that's good. When is going to be the second test then?
I think it's gonna be I'm not sure about the second test, or you're talking about the retake,
Yeah,
right?
retake. I'm sorry.
Oh, yeah. The retake I think is gonna be on Wednesday. Like the day after we come back, I'm pretty sure she's gonna give us back our test so we can
Uh-huh.
look over it, do corrections, and then I can retake it the next day.
So next week, the Wednesday next week, right?
Yeah.
Okay. Okay, so we can quickly go over some basic concept and one more time, and so we have next actually section Tuesday. So I can maybe just I don't know if you have time to study yourself, you can bring the questions in our next session too, and I can maybe just show you some example problems, and then we can actually walk through them together Tuesday. But let me give you some basic ideas how magnetism work, and then we'll just move on to the next section. So. Did your teachers complete cover the whole topic of magnetism, or just finish some portion of it and then just test it?
Yeah, it was like this was more like a quiz more than a test.
Okay. Okay.
It was just like she taught us the first five chapters, which
Mm-hmm.
is all about like the basic equations like right hand rule
Mm-hmm.
and about like wait, let me pull up my notes real quick. I think it was like very, very basic, I think. But
Mm-hmm.
it
Okay.
was also, but the problem that she gave us was a little confusing. It was using kinetic energy and
Mm-hmm.
potential energy and relating it that to
Mm-hmm.
the to find like velocity and then to find like the distance traveled. So like the radius equation, the period equation,
Mm-hmm.
force equation. So those were like all the things that she taught us, I think.
Okay, well, in this chapter, I think all you remember is three things: moving charge and magnetic field and the force out of electric field and the magnetic field. Because once the charged particle moving under the magnetic field, it has the change of the velocity, which produce the external, I mean, extra actually force, Coulomb force on the moving charge. Plus, the magnetic field itself produce some force when the charge actually moving. So, if assuming they have like some kind of magnetic field, let's assume that the magnetic field coming out of this whiteboard, then now is have some kind of like moving charge with the total amount of charge Q, then this magnetic field itself produce the magnetic force. So that magnetic force is given by this notation. So now they're all perpendicular. The direction of the velocity, let me just give you a simple expression of the force, magnetic field, and the velocity. So if the charged particle, assume that have charge Q, moving along certain direction with the velocity v, and the magnetic field applied to the discharge with the angle theta, then the magnetic force always perpendicular to these two vectors v and the magnetic field b. So this could be expressed with simply actually just expressed with the right hand rule. So the thumb pointing same as direction of the force, and the index finger is same as velocity of the charge, and this second finger is same direction of magnetic field. So this is right hand rule. You can easily find out the direction of any part of actually this this factorial. Oops, where is it? Okay, factorial expression. So this is basically right hand rule for magnetic force. So the thumb is upward and index finger perpendicular to that force, and magnetic field direction same as the third finger. So the reason we can apply this right hand rule is because this magnetic force is the vectorial dot product, I mean the cross product of the velocity vector v and the magnetic field b. So force of magnetic field is of onto the moving charge is